Good morning, everyone. I welcome you to lecture number 2 of our course, Collective Dynamics of Firms. Last week, I gave a broad introduction into the topic. As you probably recall, this is part of the larger field of industrial economics or industrial organization or industrial dynamics. And this particular lecture focuses on data about thousands or even millions of companies and tries to find statistical regularities. And once we find these regularities, we have an interest to understand why this regularity is there. And we, of course, we would like to develop models in order to reproduce this. In order to do so, I have introduced the state-of-the-art software that we use in this course to analyze the data. This is notably the statistical software R, and your first self-study exercise was about installing R and reproducing the normal distribution. Once you have installed R, it should have taken like 60 seconds to get the picture, I hope. Today we have our first exercise. And Pavlin is ready to answer your question in case there were problems. Today, we start to introduce the topic in a more formal way. And I hope that you did not get scared about the many equations that are printed in the handout. In fact, you shouldn't be scared. First of all, I'm here to explain everything. Secondly, we do this in the formal way to help you to understand it. It does not mean that you have to reproduce every single equation from these slides, right? This is not what we have in mind. Instead, we would like to provide you with more insights about this. We will talk today about random variables and their distributions. In case you took a course in computational statistics already, there is not much new for you, but for all those who are average MTech students, we found it useful to recapture some of the basics here. And we will introduce 2 classes of distributions today that play a role through the whole course. These are the symmetric and the skewed distribution. In particular, you will learn how to measure skewness, and you will also learn how to determine specific parameter dependencies of these distributions. So, let me go back to the examples that we used already last week. We would like to understand how firms grow. And this means that we first have to have a proxy of the firm size in a given year. And then we need to have data about the firm size in different years. And only then we are able to estimate the growth. So the question that is also to be answered in your second self-study task that is distributed today is how much does the firm size vary between 2 consecutive years? Because that's needed to understand what growth means. And a particular question that we will then answer in more detail also in the next lecture is, if we find that the growth rate, if we have determined the growth rate between 2 consecutive years, the question is, does the growth rate depend on the size? Or does it not depend on the size? If it does not depend on the size, it means that your small startup company has the same probability to grow as a big company like Nestle, for example. So you can think of this for a moment. Is it true or is it not true? If it depends on size, then we would like to know how the growth rate of a company scales with its size, right? So these are things that we will answer in the lecture and also in the self-study talks. The first step is we need to get the data. There are various ways of proxying firm size. And I will discuss some of these during the lecture. For the moment, it is sufficient to assume that we proxy the firm size by the number of employees that a firm has. But you can also think of other proxies of firm size. Maybe you have a few other suggestions. How can we measure this? Capitalization, right? So that's one. Revenue, yes. So other ideas? Okay. So we will discuss a few, for example, sales is another measure, right? We will discuss some of these proxies, I think, the next lecture or so. The interesting thing I can already tell you is no matter what proxy you use, you'll see more or less the same pattern. So that's why we are quite robust in our assumptions that we proxy it with firm size with number of employees, and that's it. Yeah? So we already did the first step for you. We queried the database that I introduced last week and have provided you with 10 to the 4 data entries about firms in 2 consecutive years. And now we talk about step number 2. We have to analyze the data. So the data is given to you now, and we would like to look into this data. And the first question we have to answer, what is the distribution of the firm size and the firm growth rate that is underlying this data? And that is the question I would like to discuss with you in today's lecture. To discuss this, we need to start a bit more in the formal way. We depart from the specific idea of the firm size and talk about random variables in general. The nice thing about this is once you move to a different field, you talk about stock market data, you talk about biological observations, whatever, right? You can still use the knowledge that you acquire from these slides, right? So this is not specific about firm size. This applies to any sort of random variables. So we assume that the data that is given to us in this little data file that we provide today is drawn from a distribution. So that's a random draw. There's a distribution underlying this data. We do not know this distribution yet, but we assume that 10,000 times someone makes a random draw from this distribution and gives us a number back, and these are the small numbers xi. So what we have is we have a data stream of xi, x1, x2, x3, pum, 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 and then we have x1, x2, x3 for the next year again. So, and our assumption is these are random draws from a particular distribution. And in order to find what was the distribution, we start by proxying the distribution with a histogram. So that means we try to plot the frequency at which particular x occur. And I have sketched it here in this little diagram. So we have here the x values distributed. And then you see in the gray bars the frequencies of these x values. And you see that, of course, there is not a perfect match between the observations and the underlying distribution. And that's exactly the problem. We have to talk about how to statistically get information about the underlying distribution if the pattern that we get from the frequencies looks like this. Our observations about firm size refer to discrete variables. You have either 2 employees or 3 employees. You do not have 2.5 employees, right? Therefore, we have to talk about discrete variables first, but later I will repeat the same story also for continuous variables. Why is continuous variables, why are they useful? Because we can do some analytical approximation that are not that easy to get from the discrete variable. But our observations are assumed to be discrete variables. right. What happens? Huh? Oh, goodness. So, press the wrong button here. So, this looks a bit, yeah, mathematical or maybe messy, if you like. So, it is only thought to help you to go formally to these things. If you don't like math, then you skip all these equations, just listen to my explanation, right? So, okay. In order to describe the probability distribution of our variables, we have to introduce two different notions of the probability distribution. The first is called the probability function or probability mass function in mathematics, and the second is called the cumulative distribution function. So, and the latter one is just the sum or the integral of the former one. So, okay. What is the information we get from the probability mass function? It tells us how probable it is that I find a given value xi that is in realization of the random variable x. So that means the small f of x gives me the probability, more or less, that the random variable capital X has exactly the value xi. That's the meaning of it. Here's one example. Of course, we have to think of the sample space of the possible outcome. So, what is the sample space of the possible outcome for firm sizes? Any idea? Right. So, okay. First of all, it starts with 1. We don't know what the maximum number is, but a good proxy is the world population, for example, right? So it shouldn't be much more than 10 to the 9 or so, right? So, okay, so that's the lower and an upper bound. There are discrete values. And most importantly, none of these values is negative, right? Also very important. Here's another example, much simpler. We toss a coin, and then the sample space is only 2 possible outcomes, namely tail or head. So we call this 0 and 1. And then we tell about the probability that 0 occurs or the probability that 1 occurs, and each of them, as you know, is just 1/2. Okay. That's the meaning of the probability distribution. The cumulative distribution function, which is sometimes only called the distribution, is the capital X, the capital F of X. And this gives you the probability that a value randomly drawn from the underlying distribution function is below a given value xj. For example, we talk about income, right? Then the capital F gives you the probability that your income is below 1 million francs, right? So that is the information. You already see that this does not contain all the information. It gives you just an upper limit, right? And the probability that the income of a Mr. X, who is the CEO of a company Y, is below 1 million francs is, of course, much smaller, right? So, okay, so it really depends on the underlying distribution function. Okay, and what we do here is we sum up all the values of this probability mass function up to this level, xj, here, and the cumulative value, that means the sum of all of these, gives me this probability. So in the example of flipping a coin, then it's very clear. You have these 2 realizations here only, and together they have to sum up to 1 because there is no other value available, right? So you just recapitulate. The small f gives me the probability that a certain xi occurs, and the capital F gives me the probability that the value I get is below a certain value, xi or xj. So, now that we know this definition of the distribution, we have to ask ourselves, how can we characterize the distribution? I mean, we have to give a formal expression. So, and we characterize it by two parameters which play a major role, although in the course. One is called the mean value mu, and the other one is called the variance sigma square. The issue here is that I do not know the mu, and I do not know the sigma square. All I know is a sequence of empirical observations, and then I have to calculate the mu and the sigma from these empirical observations. And that's described here on this slide. So we assume that a good proxy for the mean value is just the arithmetic mean. So I sum over all of my observations, 1 to n. I divide by n, and that's the mean value. How do I get this? We talk about it later, right? So this sounds natural to you. What else should the mean value be, right? That's the most obvious thing. That's wrong, right? So the mean value can be defined in different ways. I think I wrote a bit in the notes, yes. There's also the geometric mean, right? Which is a much better proxy for the mean value in certain circumstances. We come to examples in the next lecture, actually. So this is a proxy for the mean value, just the arithmetic mean, and the variance is then the deviation from the mean. And because it's squared, we square it here. So once we know the mean value here, so then we calculate the deviations and we scale it by 1 minus n. So we come to this 1 minus n later again. N minus 1, sorry. Yeah?
I have a question, sorry.
Yeah.
So capital X
Yeah.
bar should be mu hat, actually.
In this particular case, yes. So in other cases, not. So it depends a bit, yes. You are right. In this particular case, it's the mu when I write it like this. Yeah. Because I have defined it like this. But as I said, the mean value is not the average. So that's the average. So that's very important. Therefore, I took a capital X bar here. So that's the average, and this is the mean value. For the moment, you can assume that's the same. But we come to other examples where it's not the same later on. So, okay. So we use these variables with a head to remind ourselves on the fact that these are proxies of true values that we do not know. Why don't we know these true values? Because we don't know what the underlying distribution is, right? So we just have a finite sample set, 10,000 values, and we have to calculate it in some way. Okay. Now I come to the same, but just for continuous variables. As I said, in the observations, we do not deal with continuous variables, but it's helpful to have an analytical expression. So, and then I can proxy the probability density function, PDF, here by a continuous function. And the f of the small f, x, is the probability that I find this value x, which was the xi in the discrete picture, in such an interval between t and t plus h. H is a very small number, right? So there is a lengthy discussion. I think I also wrote it in the notes here, that we should not call f of fx a probability, and so on, right? These are mathematically valid restrictions of our discussion, but this is not a course on mathematics, so therefore we skip this discussion here, right? It is just for you a reminder. There can be a deeper discussion underneath the whole topic, but we skip it here, right? So this basically gives you somehow the probability to find this value x. And the cumulative distribution function, as I said, is nothing but the sum up to a given value x, and or here in this particular case t. So that means it's the area under this function, right? So this is very obvious. We have two notions: the probability density function and the cumulative distribution function. And as I said, the latter is just the sum or the integral of the former. Yeah, that's it. And we try to characterize the probability density function for two variables. The first one is the mean value, and the second one is the variance. And for the discrete case, I gave you a proxy how to get this from the data, right? All right. So now, how do we proxy the mu and the sigma square from continuous variables? So then, of course, we have a similar notion here compared to the discrete case. In this particular case, we call the mu the expectation value, and it's simply the x times the probability to find this x. So integrated over the whole sample space, or it's not the sample space, it's a continuous space now. Right? And the variance is calculated likewise as a deviation from the mu. And the standard deviation, it's another term that is often used instead of variance. It's simply the square root of the variance. Sometimes I mix this up, yeah, when I talk about standard deviation, but you know what I really mean, right? Either the sigma square or the sigma, right? There's a firm relation. So that's a formal definition of mean value and variance for the continuous space. We need to keep this in mind that it is well defined, or we will have to deal with the issue how to estimate it from the discrete variables. So now we start with one example, and like in school, we start with the most simple example, that's a normal distribution. So when I thought about this, I wanted to have an example that is not totally boring. So, and then I came up with this idea of a shoe company, right? So, which I called the 3S company. So, but it is a good imagination of how to apply what we learn about distributions to a very simple case. So let's assume you are the manager of this shoe company. So, and you want to produce shoes for the European market. So the total market size is more than 700 million people. So it's certainly worth the effort to think about this market, in particular since the people obviously have the money to pay for the shoes, right? So you produce the shoes in China, and you have to tell your manufactory in China how many shoes of what size they have to produce, right, in order to ship this to Europe. And that's exactly the question. So how can we know that of shoe size, how many pairs of shoes of size 20 or 24 or 30 we have to produce? That's the question here. So then we go and do a little research on the literature. We found this paper from a Japanese website where people thought about how shoe size distribution is looks like, and we found that it's a normal distribution with the mean and the standard deviation, not the sigma square, but the sigma only, given by these values. And obviously, there is a gender difference between man and woman. You could have guessed from the outset. So this is all that we know now, and we would like to apply this to our question: how many pairs of shoes of what size do we need to deliver to Europe? Right? That's the question. Okay. Let me just plot the function first. You did it already in the exercise, right? First self-study exercise. Everyone got this picture here. It is obviously not only helpful, but also needed that you remember how the probability density function of the normal distribution looks like. Would be good if you are able to write down this equation, right? So you see it's a very simple structure here. It's an exponential function. In the exponential function, you have a square here in the sigma and also in the first part here. And this is the difference between x and mu, where mu is the mean value. And this is simply the variance here. And then there is a normalization factor, which is the 2 times sigma square root, and an additional pi here. We are not deriving this, but you should remember this from the structure, right? So first the exponent, then what's in the exponent, something with the square, and then a normalization factor, that's the square root of this denominator here, together with an additional factor. So that's how it looks like. It's obviously a symmetric distribution. That's the first thing you have to notice. It's a symmetric distribution, and the way we plotted it is symmetric according to 0, but this is because we assumed that the mu is 0 here. So it's symmetric according to mu, actually. Very easy to understand. So now we have to talk about the cumulative distribution function that I already introduced, the capital F. How do we get this? By doing the integral of the distribution function, right? Of the small f. I explained it to you. So now you start and do this, and then you recognize, okay, there is very quite complicated or intricate outcome. So there is no closed form solution for the cumulative distribution function of the normal distribution. So therefore, people, until very recently, calculated this once. They printed it in tables, and then you go and look up the value for a particular x in the table. That's what I did when I was a student, for example. Today, everyone is doing it with a computer, of course. Yeah? But we always had these tables. Okay. In order to look it up in a table, we face a problem. Of course, we have a particular mu and we have a particular sigma square. So they will not be able to print tables for all sorts of mu's and all sorts of sigma square, right? Therefore, we have to normalize this distribution. We introduce a normalized variable, that's a t, by just subtracting the mean and dividing by the sigma. By this, we get a normalized normal distribution where the mean is 0 by definition and the sigma square is 1. That's a very important normalization. And this, only this function is printed in the table, right? This is sometimes also denoted as capital phi of t. So let us take an example here. Let's assume the mu is given as 4, sigma square is few, and our t is 3. So then we know that our underlying normal distribution looks like this. And now we have to rescale it by just doing this transformation. So in order to get from here to the phi, we have to subtract the 4 here and the 2 divide by 2. And then we have the normalized distribution, and we go and look it up in a table. I doubt that anyone still had these table books, right? No one has it. So therefore, we use the same in R. Yeah? In R, it takes us like 15 seconds. So, of course, we have to tell R what's the mean value. Mu is 4. What is the sigma? Not the sigma square. The sigma is 2. And what is the t? 3. And then we type p norm, which is the function calling the normalized normal distribution, like this. And so R returns this value to us. So, and because we talk about the cumulative distribution function, so the interpretation of this value is very easy. The probability that a value x is less or equal to 3 is about 40%. That is the message that we get from this. I hope you could follow up to here, right? So now we go back and want to ask how many shoes of what size do we need to produce for the European market, right? So, okay, I have plotted here the two distributions for men and women. Recall they are both normally distributed, but with a different mean and a different variance. Yeah? So these are the two distributions. And now we recall that we are able to calculate the cumulative distribution function. This tells us what is the probability that a value is lower, that the value that we randomly draw is lower than a given value. Yeah? Okay? Let's assume we are interested in shoe size 21 here. And we asked, what is the probability that the shoe size is below 21? So. And this can be calculated as I have described before, right? You normalize it, and then you go and calculate it from R, by using R. So, but this gives us all people that have a shoe size up to 21, right? So, in order to know how many people really need 21 and not 20 or 19 and so on, we have to subtract how many of these people have a shoe size that is less than 20, right? So, because we are only interested in those people who really need 21 and not in all people that need something below 21. And then we calculate this, and then we get this kind of numbers here. So that means the cumulative distribution functions help us to give an upper estimation of how many pairs of shoes people in Europe need, right? So this is exactly the number of shoe pairs that we have to produce of a given size. Everything clear? Yes, very good. There is a question at the very end that you have to calculate this for other values of the shoe size. And I want you to do it exactly as I have described on the slide here. Yeah? Once you understood this, it takes you like 30 seconds. Yeah? 15 for the upper limit and 15 for the lower limit, right? So not more. Okay. Now that we have answered this question, we already found out what is the difference between the two different genders, male, female. And in order to have a better understanding of the whole thing, we would like to remove this gender difference from the distribution. In the case of the normal distribution, it's very easy because we already discussed how to normalize or how to scale a normal distribution. That was 2 slides before, right? So, which is the standard normalization. So, remember that from the values of x, I have to subtract the mean, and I have to divide by the standard deviation. You know? This was given 2 slides before. So, and this means that instead of having a distribution from which I draw all the numbers for the females and then a distribution from which I draw all the numbers for the males, I now have just one distribution, namely the normalized distribution that describes both males and females, right? Because I have normalized this. And the result of the result of this is shown here. Instead of having this picture, where I have these 2 distributions, I only have one picture with one distribution. And what has changed between the two between the two pictures here? What has changed? No one is recognizing it? Please, Mrs. What has changed between these two pictures here? Excuse me? The height has changed. Oh, this is okay. It's a bit. The axes have changed. Correct. So the axes have changed. The x and the y-axis have changed. So I was able to merge the different distribution in one master curve. Once I got the right scaling idea about what is the new x and what is the new y, right? So that means instead of talking about different distributions for different genders, or later talking about different distribution of growth rates for small firms and big firms, that was the example we already used, we talk only about one distribution, but this needs to have the right scaling of the x and the y-axis. Once I know what I have to write here, everything collapses in one curve, right? But then I can claim that I understood the problem because I found the common denominator of all of these, and I found the correct variable that describes all of these distributions. It's a very important point for you to make. Yeah? So, okay. So we have a scaled variable here and a scaled variable there. And this allows us to collapse different distributions to one master curve. That was correct. Did you get this? I hope so. This is a bit complicated way of writing it up. It simply means x minus the mean value divided by the standard deviation. Yeah? So that's basically the t as it was defined before. Everyone got this, I hope. We will talk about these scalings quite often in the course, so therefore I want you to think, how do you get from here to there? So again, the conclusion is we understood the role of gender here. What's the difference between these two? And because we understood this, we were able to remove the influence of gender from these two curves and make it one curve that is completely independent of whether we talk about males or females here. That is the important step we did in the analysis. Okay. There is another problem underlying the whole thing, which I just address here. We will talk about this in the next lecture in more detail. It's about data binning. Remember that we talk about discrete variables here, and therefore we have histograms that have this defined height and defined width. And of course, the histogram is very much dependent on how we define the bin size. I have plotted the same data here 3 times. The only difference between the 3 ones is the bin size. It's not the data, it's the bin size, right? So I took my observation and then I fitted this here. I have much more bins, so then I get a distribution like this that looks more or less symmetric, right? Then I choose a larger bin size, only 21, 22, 23, and so on. Yeah, bin size of 1 centimeter. Then you see this distribution has lost its symmetric shape. Why is this? Because I have chosen a bin size that is too large to show any sort of symmetry here. And then I have chosen even a larger bin size, namely 20 to 24, and then I get something like this. This looks like a uniform distribution. Why is this? Because I have chosen a bin size that is way too large for this problem, right? So therefore, everything looks like the same probability. this addresses the question how to get the optimal bin size to bin the data. You can also think of something differently here. You can think of having a very, very small bin size, 1 millimeter or something like that. What would be the outcome then? So, or even a tenth of a millimeter or something like that. You also end up here with something that's more or less uniformly distributed, because for every single realization that you find, you have also defined a bin. So that means the height is 1 in every bin, right? Because you made such small bins that I can distinguish myself from another observation, right? So you have more or less equal bin size. So that means you should not choose a bin size too large, but also not too small in order to get some statistical information out of this. How to choose the optimal bin size will be discussed in the next lecture, but I want you to already anticipate the problem here. Because if you get a picture like this, which I show in the middle, you would obviously assume that we talk about skewed distribution here, so where most of the mass is concentrated to the right. No? That's the consequence of this. So the nice answer to this is R is already choosing the right bin size for you. So you do not need to care about it. But I want you to understand this problem, right? So if you use R, then this is already optimized without you knowing it. Okay. Now let's go back to the histograms that we need to calculate, for which we need to calculate now the two parameters, right? We still need to know if we have the observations here, then we need to calculate our distribution and the mu and the sigma. Okay, you can remind me that I already gave you the mu and the sigma, correct? So this was thanks to some guy who published it in the internet. In general, you don't know the mu and the sigma, you have to do it yourself. And therefore, we are addressing this here. So we have 1,000 measurements of the foot size, and then we get these numbers here. And then we plot the histogram, number of times observing a given value, divided by the total number of observations, which is 1,000 in our case. And then we get a picture like this here. So, and now we need to know two things that are addressed here. The first thing is we need to know what are the two parameters that we need to have to characterize the distribution. It was a mu, the mean value, and the sigma square. I have to calculate these. But the other problem also is I have to know whether this histogram that I just showed you follows a normal distribution or another distribution. If it follows another distribution, for example, a log normal distribution, then it's not clear that the mu and the sigma are calculated the same way, right? So I said that because you got so much used to the normal distribution, you can only think of the mu and the sigma at the arithmetic mean and the respective variance, right? So, but there are other cases. I want you to understand that this is like the hen and the egg problem, right? We can decide what we want to choose first to solve, but we have to keep in mind the other one. So we will talk about the mu and the sigma square first, assuming that we have a normal distribution. But later, we also have to answer the question, do we have a normal distribution? Is the data telling us that we have a normal distribution? Or is it just our lack of imagination that we think we have a normal distribution because we don't know about other distributions? Weibull distributions, pam. There is a whole zoo of these. Yeah? So, you understand? We have to solve these two problems together, and we do it step by step instead of solving it together. We first talk about the first problem and then about the second. So now the bell is ringing. Exactly. So That means after the break is 10 minutes. Yeah? 10 after 11, we continue with the lecture. 10 after, no matter whether there's a gong or not, 10 after 11, we continue, 10 minutes. Yeah? And then I continue with this one. So let us please continue with lecture number 2. By the way, all the material is available on Moodle, as you know, and this is a password for the registered students. I have put it up on the blackboard again. You can log in, you find the handout of the lecture, you find additional literature that is thought to further educate you, and you also find the self-study tasks and the data to download, and you find a link to the recording of this lecture as well. This recording is very nice, so if you forgot what was the meaning of a particular slide, so then there is a slider and you go to this particular slide and then you hear me hopefully telling you the right thing. Right? So it's a very convenient way. The drawback of this very convenient way is that many students are absent, you know, because they no longer feel the need to sit here. You know? So that's the problem. So from the registration, there should be more than 20 students in this course. Okay, let me now continue with this issue of parameter estimation. We need to know how do we calculate the mu and the sigma. For the normal distribution, I gave you this example already. That means you know what is the result. But now we ask the question, if we do not know the result, how can we get the result? How can we find an equation to calculate mu and sigma? That's the task here. We need to find parameter estimation for the mu and the sigma, and how do we get this? And the method that we use here is the maximum likelihood estimation. I'm sure that some of you have already heard about this. Can you just raise your hand if you are familiar with the 1, 2, 3, a bit, yeah? Okay, okay, so then I can be very quick, but let's assume that those who look into the video recording have not the same skills. Yeah? So therefore, I put it here. So we have this realization of the random variable x, and these, Alex, you can take a note. These are supposed to be small x, yeah, if we want to be consistent with the previous slide. So these should be small x, and capital X is just the name of the random variable. So we assume that these variables are IID, that means independently and identically distributed. This is an important assumption when we talk about random variable. Random means random as opposed to correlated, right? So if you draw a number, then the draw should not depend on the number you have drawn before or the number you will draw in the future or something, right? So if this is the case, then we talk about correlations, and then we do not talk about independently distributed variables. And identically distributed means if I have 1,000 of these realizations, I assume that they are drawn from the same distribution and not 500 from one distribution and 500 from another distribution. This is the meaning of this. You can circle this in. It's a very important assumption. If you go to econometrics or courses, then of course this is a standard assumption that you find everywhere, but you should understand what the meaning of it is. So, and now we would like to discuss how do we get our parameters mu and sigma for the foot lengths. And our distribution is assumed to be a normal distribution. That is not clear. I mentioned to you there is a related problem where we test the distribution. Is it a normal distribution? Now we assume it's a normal distribution, and then we calculate the mu and the sigma, and then we go and test whether this fulfills the criteria of the Kolmogorov-Smirnov test. And if it does not fulfill this criteria, then we have to go back and say, well, maybe it's a log normal distribution. And then we have to recalculate the mu and the sigma, and then we have to test the next distribution, and so on and so on. So this is the way we do this. This is just a starting exercise to get you acquainted with these methods here. Okay. We define a likelihood function. This is this capital L that depends on the two variables, mu and sigma, and is formally given as the joint density of the measured data and a distribution with these two parameters. So you should read this tilde f as a function like, given that I have the observations x1 to xn, what is the mu and the sigma that likely describes this set of observations, right? Under the assumption that it's normally distributed. That's not mentioned here, but that's another example, right? So this is how you read this. So that's the likelihood function. Okay, so now we make use of our argument that it is that we talk about IID variables here. So independently and identically distributed data. So if these realizations of the variable x are independent of each other, what have you learned in probability theory about independent events, the probability of independence event? Does someone recall this? Yes, please.
The joint probability is the product of individual probability.
Right. So if I talk about some dices, right, then the probability that I have a 1 does not depend on whether I had a 6 before, right? So that means there are independent realizations over the sample space 1 to 6. And in this case of the independent realizations, I can factorize this function into functions that no longer depend on all of these observations, but just on a single observation. And according to probability theory, the joint probability is just, as you said, the product of the independent probabilities. That's something you have already heard in basic mathematics, right? So you understand why we are able to factorize this. Yeah? Did you get it? Because these are independent distributions. And now we make use of the fact that they are identically distributed. They come from the same distribution. So that means for each of these, I assume that they follow a normal distribution. They follow all the same distribution, which is a normal distribution. So that means for the f, I make this assumption here. That's a normal distribution. And please recall that I want this to be changed into small xi, right? So you understand this? So that means we have a product of all these normal distributions here. That is due to the fact that the variables were independent. The product comes from this. And they are identically distributed. That means they are all the products of the same normal distribution here. This is the message of it. So that means I have already an expression for my likelihood function. And even if it looks complicated on the first glance, it is not complicated at all. This is a normal distribution where I want you to repeat and recapitulate the equation, and this is just a product over a number of realizations. Okay? So then we ask ourselves now, what are the parameters mu and sigma that describe this likelihood function the best? That is the next question. Yeah? So, what are the parameters that describe your data? There can be different mu's and sigma that fulfill the likelihood function, but the question is what describes it best. So, and this is equivalent to the question of finding the maxima or the minima or the extrema of a given function. So, you know this already from your courses in mathematics, basic mathematics. If you want to determine the maxima of a function, what do? Yes, so you take the first derivative and set it to 0, right? So that is the same thing we do here. We take the first derivative of the likelihood function and set it to 0. So now the likelihood function depends on two parameters, mu and sigma. So we have two derivatives here, which we have to set both to 0, right? Okay. Now we are facing the problem that the likelihood function is a product of a number of normal distribution, which is okay, but makes it a bit difficult to handle. So therefore, we say if we take the logarithm of the likelihood function, this will probably not change the maximum, right? So, but it makes the things more convenient if we take a logarithm of a product. This turns all the products into sums. That's a nice thing. Therefore, we take it, right? So, yeah. Instead of having our likelihood function with the product, we take the ln of the likelihood function, which is a small l here, and this turns all the products into a sum. That's a nice feature then. And then it looks like this. It's a sum over the ln of all these things. So, and you see there is the ln of the prefactor, and there is the ln of the exponent. And the ln of the exponent is simply what we had in the exponent here. Right? Yes, please.
Shouldn't the whole expression be in parentheses, like sum over both terms?
Where? Here?
Yes, here you open parent and then you close it after the second term.
No, this is the ln here, and the ln is already taken from here. And the sum goes over the whole part here. Is this your question?
Yes.
Yeah, of course. I mean, why do you assume that the sum applies to the prefactor? The prefactor does not depend on I. This is a variable that depends on I. Yeah?
Yes.
I could, if you like, can also write the sum here, right? So, yeah. But again, so this was how it looked like. So, I take the logarithm of this, and this means the logarithm of the prefactor and the logarithm of this, and the logarithm of an exponent something is simply what we have here, right? So that's how we got to this equation. And now we rewrite this a bit in a more convenient way, like this. Yeah? So this is the same to get it to here. I do it step by step to really show you that you do not need to get scared here, right? So it's very easy to understand what we are doing. Everyone should be able to understand why we end up with this equation for the log likelihood function in case of a normal distribution. Okay. You agree. So, and now, once we had defined the log likelihood function, we have to take the partial derivative, and then we have to set them to 0, right? So let's take the partial derivative from the previous slide. So, log likelihood function derived after mu. So, is there someone who volunteers to talk about this here? No, it's too easy, right? So, everyone understands this. So, we go and look, yeah? So this is the equation. This doesn't depend on mu, this doesn't depend on mu. Only that depends on mu. So therefore, we get this as the derivative, right? So, and we can rewrite it in this way. And the same is true for the derivation after sigma. This doesn't depend on sigma, this depends on sigma, and this depends on sigma. So therefore, we get a first term. This is 1 over sigma, and the sum is, there are n sums, so that because there's n times 1 over sigma, we get the n here, and this is the second term. that we get from this previous exponent, right? So very easy to understand. And then last step, we set this to 0 and solve. So then we have two equations which both depend on sigma and mu, and we have to solve two equations for two variables. I hope everyone is able to do this, right? And this is the result. The result is not a surprise, right? What you see here is that the mu that maximizes the likelihood of describing the data that I have given to you is simply the arithmetic mean with a small x here, right? So it's not a big deal, right? So I told you the result before. But now you can assume that you didn't know the result before. Then this is the way to calculate this. We come to the log normal distribution afterwards. And you need to get an estimation of the mu, and this estimation looks completely different. Yeah? And then you go to Wikipedia and they just print this for you. Right? And then you ask yourself, oh, how did they get this for the mu? And you understand how they got this for the mu by doing exactly the same thing, just not with the normal distribution, but with the log normal distribution. And if we want to test a whatever distribution, yeah, stretched exponential distribution, other things, then we do the same thing. We have an equation for the distribution, and then we check what is the expression for mu and sigma that maximizes the likelihood that this data is described by that kind of distribution function. Is everyone understanding what I'm talking about here? It's a very important step. So, and for the sigma, we get the same as we have defined for the sigma. And you all know the result because we started from telling you this. Yeah? But you also have to understand that the mu and the sigma look completely different if I'm not talking about the normal distribution, but for example, the log normal distribution. We come to this in a moment. I also want you to understand that there is a difference between the estimators, that's something we get from the data, and the true values. The true values are those that have not anything here on top, no tilde and no star or something like this, right? So here our start values are the same as the one with the head, which I gave you before, right? But the true values, these are values we cannot know. These are values we can only derive from a mathematical expression. Here we derive this from data. No? Okay. So with this, I come to the more interesting distributions. Recall that the normal distribution was just an exercise to tell you about the probability distribution, the cumulative distribution, and the maximum likelihood estimations to get the mu and the sigma. Now we are dealing with the real thing. The real thing is the distribution is not symmetric, but it's skewed in some way. What do we mean by skewed? It's either lopsided to the left or to the right. So then we talk about a negative skew or a positive skew. So here you see that in a negative skew, we have the left part drawn out here, and in the positive skew, we have the right part drawn out to this. Yeah. So the first question is, how can we describe the skewness? Is there a measure for the skewness? So before we calculate the skewness, let me just talk about a few properties of the skew function. So, okay, if you look here, then you see if you calculate the mean by the arithmetic mean, then you will probably end up somewhere here, right? But that's not a good proxy because very many data can be in this longer tail of the skew distribution, right? So that means you have a low mean as compared to the maximum value of this distribution. That's not true for the normal distribution. In the normal distribution, you find something that is more or less close to the mean, right? Even if it is like a factor of 2 or a factor of 5 or something. So, but here you can find something that's a factor of 100 away from the mean. That's the first thing that you see. Yeah.
Is it a problem that the distribution is not normalized anymore in the picture?
One more picture. Where is it not normalized?
Yeah, when we have the normal distribution, which is the dotted line, that's
Yeah. No, the normal distribution is not the dotted line. Yeah, it could be, yes, but okay.
But is it a problem that it's not normalized anymore? Otherwise, the height would be much lower. I mean, for measuring.
No. This is simply a sketch. Okay, you are right that this is not a normalized distribution because, okay, what Alex is telling us likely is if we normalize this thing, so then normalize means the area under the function is normalized to 1. So then this would be the normal distribution. And if I had a skew distribution, then it would look like this, right? That's what you're talking about. Yeah, so, okay. And this is not normalized, just to give you an impression of the skewness, a better impression of the skewness, right? But of course, skew distribution are in many cases also normalized. Okay, here are some properties of skew distribution. I said already there's a low mean value. Low means compared to the maximum value that you can observe. And we all often have data without any negative values. The example that we already talked about was the size of the firm, which cannot have negative value. Your wealth can also not have a negative value, even if your bank sees it differently. Yeah? So, okay. There are other distributions that do not have negative values. And there are two prominent examples for skew distribution, which we discuss in this course. There is the log normal distribution and the power law. And we now need to characterize these two distributions, the log normal and the power law. But before we characterize the log normal distribution, power law will be discussed in the next lecture. We discuss how to measure the skewness. So in order to get this, remember that we have our observed data from 1 to n. And we can calculate a skewness parameter, which we call gamma here, from the sample by having this observed mean value and the observed variance in this way. So the gamma is defined as the third power of the mean divided by the third power of the sigma. So the sigma is just here the square root of our observed variance. This was the observed variance. So, and we have to take the third power of this, and the mu was given here by the mean. So, and then we get one number back, and if the gamma is equal to 0 or very close to 0, then we talk about a normal distribution or a symmetric distribution. And if it's negatively or positively skewed, then we get this in terms of considerable numbers here. So, and here is a little example how you calculate this in R. I'm not going to retype this for you. Sometimes I did, yeah, but today I'm not going to do this. it's very easy. You just write down what's written here, and you try to understand what we do here. So we have a table with our test data. Yeah? Then we assign the values 1 to n from this test data, and we define a function that is called skew, exactly as we have described here. Yeah? So there is the m, which we call mu3 here. It is simply the sum over x minus mu to the power of 3 divided by n, and the sigma as the square root and the third power of the variance. And then we calculate this. Yeah? So very easy to understand, right? So you learn a bit of R here. Yeah? So we first define the m, the s, and then we divide the m by the s. That is how the function skew or gamma is defined. And then I just run this function on my sample. That means I read in all this data, and this is the number I get. So what's the result of this? Who's able to follow our explanation here? 1.37. There is a skewness, so it's very different from 0. And to what side? Too difficult, huh? Positively skewed. What is positively skewed? It is drawn out to what side? So, which one is it? Yeah, it's drawn out to the right. Most skewed distributions that we see are of this type. Yeah, so okay. So now we apply what we just learned to the first candidate of a skew distribution. That's the most important one. It's a log normal distribution. So what is the difference between a normal distribution and a log normal distribution? The difference is simply that instead of talking about x, I'm talking about ln x. In fact, I have a new variable, which is y equals ln x. So I replace my variable y here by ln x. So, and then instead of having a normal distribution, I have a distribution that is drawn out to the right and has a positive skew. And you also notice that in the normalization, there is the x, right? That's the next difference. So that means the exponent looks similar to the normal distribution, except that I talk about ln x, where there was an x before. So the denominator is the same, but in the normalization I get an extra x. Why is this the case? So that's maybe something you can check at home. You just normalize this, and then you see that because of the normalization, you can do this by variable transformation. Yeah? The y is ln x. And then you see that thanks to the variable transformation, you get 1 over x. Yeah? And that's 1 over x. This is simply the result of the variable transformation that you do here. And then you have to calculate this into the normalization. Yeah? You do it at home, and then you immediately understand this. Okay. This is a plot of the distribution function for on a normal scale, where you can notice the asymmetry or the skew. And we can also plot this, that is what we usually do, on a logarithmic scale. How should the log normal distribution look like on a logarithmic scale of x? Like a normal distribution, right? This is how we recognize that it is a log normal distribution. We plot the x scale at the logarithm, and then we see something symmetric, like in this case. That's the first indication of a log normal distribution. All right. So why do we talk about the log normal distribution here? I think, let me just check with you that I gave you one paper to read about the importance of the log normal distribution. Hmm? Yes. Where is it? Okay, yeah, okay, yeah, here. Very interesting paper on the log normal distribution. I wrote this in the note. That's a short paper that you can read to find out why the log normal distribution is so important. It gives you a whole zoo of applications of the log normal distribution. And many of the variables that are listed here that follow a log normal distribution, you would probably not have expected to follow a log normal distribution. It's an interesting thing to read. There's no math in it. Simply, it's a bit more overview. Yeah? So we have put this in our literature folder. You just download it, and there's a table that shows you all these variables. Very interesting. What was it? The time in hen breeds or something like this. Okay. There were many of these examples. So now we have to characterize our, so first of all, so you read please this little piece, yeah, to find out about the importance of the log normal distribution. So here, geology, medicine, physics, biology, always the log normal distribution appears. So what you learn here about log normal distribution is not just specific for economic data, it can be applied anywhere. So, but now we are left with the task to characterize the log normal distribution. And remember, we want to characterize by these two variables, mu and sigma squared, right? So, and now we have to calculate the mu and the sigma squared. How do we do this? You got the point already? So how do we do this? With the maximum likelihood estimation, right? So why am I not showing you this here, right? Because it's a bit more involved, a bit messier, right? And the normal distribution had the advantage that you already know what the result is. Here you don't know it, so therefore I skipped it here. We do the same thing as we did before for the normal distribution, now with the log normal distribution. Then we see that these are our estimators here. You don't find it a big deal, right? So you see, okay, mu is now the log of the x. And here sigma squared depends on the log of the x, so that's somehow trivial. It is not. It is not, right? Because what you see here, this is no longer the arithmetic mean. This is what you have to recognize here. But it is the average of the log of the x. Right? So, and this maximizes our likelihood. It means if we ask what is the mu and the sigma, that maximizes the likelihood of the log normal distribution function. If we assume that the data follows the log normal distribution function, it's expressed like this. Okay. So now we have a mu that refers to the normal distribution, and then we have a mu that refers to the log normal distribution. So how are these two related to our previous mu? In many cases, it's so maybe you already calculated the arithmetic mean of the x. So what's then the relation between the mu for the log normal and the mu of the normal distribution function? And here we have printed to you this non-trivial relation between those variables characterizing the normal distribution and those variables characterizing the log normal distribution. Simply for you to see that this is a difference, right? So, and here we have plotted the log normal distribution for various values of sigma and probably also of mu, but I cannot see it here. So, and then you see how the shape of the distribution changes if I have different values here. Right? So what you have to recognize is that the sigma has a very important influence now, which is clear because the log normal distribution is stretched very far out to the right side, as you mentioned. Yeah? Okay. There's also a nice note that I copied from Wikipedia. So the term expected value can be misleading. Yeah. It must not be confused with the most probable value. So that's something you can read at home. Okay. Now again, comparing the log normal and the normal distribution. So what makes the normal distribution so popular? So first of all, we see it in the living world. We can really observe it. Most features related to the human body are normally distributed. For example, the body height. For example, the shoe size. All these things are normally distributed. That means we observe this. Yeah? So if we observe outliers or extreme values, then we have a mental problem to see whether this is really an outlier or whether this belongs to the distribution, but it is just another distribution, not a normal distribution. That is a problem that prevented the log normal distribution from being recognized for a very long time. So, because in previous times, people automatically assumed that the most common distribution is a normal distribution. And then everything that didn't fit into the normal distribution was then considered an outlier. Now we know that the power law and the log normal distribution are as frequently observed as the normal distribution. That means if you observe these outliers to the normal distribution, this can be well fitting parameters that fit into the log normal or the power law distribution, right? So that is the important thing. In order to determine whether outliers belong to the distribution or not, you need to have a sufficient statistics. And in most cases, you didn't have these statistics before. That's an important issue. That means you do not have evidence enough to tell that this particular value that you have observed also belongs to another distribution, namely to a log normal distribution. Therefore, all these things were dropped. But now, we have the century of the wealth of data or the abundance of data. We have much more data than we ever had in the history of human life. And then we can now test other distributions with a higher significance. The most noticeable example is from the stock market, for example. So, okay.
Typical sample to see log normal or other kind of distribution.
No, you cannot. You cannot easily answer this. You have, but because it. You can estimate this frequency, of course, from a limited sample size. As you will see, so I give you these 10,000 data points, and I hope that you see a log normal distribution there, right? So, conclusion, 10,000 data are sufficient. So, but that's not the point. So if you go there, I mean, this was selected in a way that extreme values are nicely represented there. In other cases, extreme values are not so nicely represented. So, and then, of course, the statistic gets worse on the end of the extreme values where the distribution is drawn out. Right? It depends a bit on what you are talking about in terms of the example. Right? That's an important issue. Okay. There is no general answer what is a good data size for the statistic. It really depends on the sigma in particular. That's what I told you before. And the sigma is different from for most of these examples that we talked about. You can really go to this little piece of this paper I mentioned, because they have printed also what the sigma is. And you see that the sigma in some cases is really large. That means we need to have a large data set in order to find that this is a log normal distribution. In other cases, it's not that difficult. So, okay, so now we are left with our self-study number 2. We give you data, and you need to calculate the skewness of the data. I already gave you the example how to do this. Every single line of code was given there. Once you have R installed, you should be able to rewrite this and then to get the skewness of the data, right? Second challenge is you should plot your data in order to see whether this is drawn out to the left or to the right or whether this is symmetric. And then you have to use the maximum likelihood estimations to get these parameters that you need. The solution is already given to you, but you need to calculate this yourself in order to understand how this functions. I gave an example in detail during the lecture here. So this is the self-study task. Again, concluded. What you have to learn and what you have not to learn. The last point is a bit more, it's a longer discussion, basically, because in some cases there's a 1 over n when we talk about the variance, and in some cases there is a 1 over n minus 1, right? So where is the difference coming from? Does the difference matter, right? So these are all mathematical discussions. For you, in practical circumstances, you probably don't care, and that's also correct. But it could be that you are interested in whether we made a mistake in typing or setting these equations, or whether there's a deeper reason. So that means this addresses a deeper reason here. Huh? Okay. And these are the questions that you please answer to recapitulate the content of this lecture here. So you have to understand the meanings between the difference between the probability distribution function and the cumulative distribution function. That's the first thing. And then you have to calculate exactly the way I described in the lecture to find the probability of given true size 45 and 50 here. So you should also recall the equation for calculating the skewness. It's very easy. It's a mu to the power of 3 divided by the sigma to the power of 3. I mean, you probably will get this. That's something you should remember. So, and then you explain what is the underlying mechanism of the maximum likelihood estimation. And why we need to have an assumption first about the distribution before we can calculate the proper mean and the proper mean and variance. That's the idea. Next week we will talk about the opposite problem, namely how can we check whether this distribution is a normal distribution or a log normal distribution or something else, right? So that's the issue of the next week. With this, I thank you for your attention and remind you on the exercise that happens today at 5 o'clock. Thanks. The underlying distribution. And that's exactly the problem. We have to talk about how to statistically get information about the underlying distribution if the pattern that we get from the frequencies looks like this. Our observations about firm size refer to discrete variables. You have either 2 employees or 3 employees. You do not have 2.5 employees, right? So, therefore, we have to talk about discrete variables first, but later I will repeat the same story also for continuous variables. Why is continuous variables why are they useful? Because we can do some analytical approximation that are not that easy to get from the discrete variable. But our observations are assumed to be discrete variables. All right. What happens? So, press the wrong button here. So, this looks a bit, yeah, mathematical or maybe messy, if you like. So, it is only thought to help you to go formally to these things. If you don't like math, then you skip all these equations, just listen to my explanation, right? So, okay. In order to describe the probability distribution of our variables, we have to introduce two different notions of the probability distribution. The first is called the probability function or probability mass function in mathematics, and the second is called the cumulative distribution function. And the latter one is just the sum or the integral of the former one. So, okay. What is the information we get from the probability mass function? It tells us how probable it is that I find a given value xi that is in realization of the random variable x. So that means the small f of x gives me the probability, more or less, that the random variable capital X has exactly the value xi. That's the meaning of it. Here's one example. Of course, we have to think of the sample space of the possible outcome. So, what is the sample space? We are quite robust in our assumptions that we proxy it with firm size with number of employees, and that's it. Yeah? So we already did the first step for you. We queried the database that I introduced last week and have provided you with 10 to the 4 data entries about firms in 2 consecutive years. And now we talk about step number 2. We have to analyze the data. So the data is given to you now, and we would like to look into this data. And the first question we have to answer, what is the distribution of the firm size and the firm growth rate that is underlying this data? And that is the question I would like to discuss with you in today's lecture. To discuss this, we need to start a bit more in the formal way. We depart from the specific idea of the firm size and talk about random variables in general. The nice thing about this is once you move to a different field, you talk about stock market data, you talk about biological observations, whatever, right? You can still use the knowledge that you acquire from these slides, right? So this is not specific about firm size. This applies to any sort of random variables. So we assume that the data that is given to us in this little data file that we provide today is drawn from a distribution. So that's a random draw. There's a distribution underlying this data. We do not know this distribution yet, but we assume that 10,000 times someone makes a random draw from this distribution and gives us a number back, and these are the small numbers xi. So what we have is we have a data stream of xi, x1, x2, x3, pum, 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 and then we have x1, x2, x3 for the next year again. So, and our assumption is these are random draws from a particular distribution. And in order to find what was the distribution, we start by proxying the distribution with a histogram. So that means we try to plot the frequency at which particular x occur. And I have sketched it here in this little diagram. So we have here the x values distributed. And then you see in the gray bars the frequencies of these x values. And you see that, of course, there is not a perfect match between the observations and of the possible outcome for firm sizes. Any idea? Right. So, okay. First of all, It starts with 1. We don't know what the maximum number is, but a good proxy is the world population, for example, right? So it shouldn't be much more than 10 to the 9 or so, right? So, okay, so that's the lower and an upper bound. There are discrete values. And most importantly, none of these values is negative, right? Also very important. Here's another example, much simpler. We toss a coin, and then the sample space is only 2 possible outcomes, namely tail or head. So we call this 0 and 1. And then we tell about the probability that 0 occurs or the probability that 1 occurs. And each of them, as you know, is just 1/2. Okay. That's the meaning of the probability distribution. The cumulative distribution function, which is sometimes only called the distribution, is the capital X, the capital F of X. And this gives you the probability that a value randomly drawn from the underlying distribution function is below a given value xj. For example, we talk about income, right? Then the capital F gives you the probability that your income is below 1 million francs, right? So that is the information. You already see that this does not contain all the information. It gives you just an upper limit, right? And the probability that the income of a Mr. X, who is the CEO of a company Y, is below 1 million francs is, of course, much smaller, right? So, okay, so it really depends on the underlying distribution function. Okay, and what we do here is we sum up all the values of this probability mass function up to this level, xj, here, and the cumulative value, that means the sum of all of these, gives me this probability. So in the example of flipping a coin, then it's very clear. We have these 2 realizations here only, and together they have to sum up to 1 because there is no other value available, right? So you just recapitulate. The small f gives me the probability that a certain. Good morning, everyone. I welcome you to lecture number 2 of our course, Collective Dynamics of Firms. Last week, I gave a broad introduction into the topic. As you probably recall, this is part of the larger field of industrial economics or industrial organization or industrial dynamics. And this particular lecture focuses on data about thousands or even millions of companies and tries to find statistical regularities. And once we find these regularities, we have an interest to understand why this regularity is there. And we, of course, we would like to develop models in order to reproduce this. In order to do so, I have introduced the state-of-the-art software that we use in this course to analyze the data. This is notably the statistical software R, and your first self-study exercise was about installing R and reproducing the normal distribution. Once you have installed R, it should have taken like 60 seconds to get the picture, I hope. Today we have our first exercise. And Pavlin is ready to answer your question in case there were problems. Today, we start to introduce the topic in a more formal way. And I hope that you did not get scared about the many equations that are printed in the handout. In fact, you shouldn't be scared. First of all, I'm here to explain everything. Secondly, we do this in the formal way to help you to understand it. It does not mean that you have to reproduce every single equation from these slides, right? This is not what we have in mind. Instead, we would like to provide you with more insights about this. We will talk today about random variables and their distributions. In case you took a course in computational statistics already, there is not much new for you. But for all those who are average MTech students, we found it useful to recapture some of the basics here. And we will introduce two classes of distributions today that play a role through the whole course. These are the symmetric and the skewed distribution. In particular, you will learn how to measure skewness, and you will also learn how to determine specific parameter dependencies of these distributions. So, let me go back to the examples that we used already last week. We would like to understand how firms grow. And this means that we first have to have a proxy of the firm size in a given year. And then we need to have data about the firm size in different years. And only then we are able to estimate the growth. So the question that is also to be answered in your second self-study task that is distributed today is how much does the firm size vary between 2 consecutive years? Because that's needed to understand what growth means. And a particular question that we will then answer in more detail also in the next lecture is, if we find that the growth rate, if we have determined the growth rate between 2 consecutive years, the question is, does the growth rate depend on the size? Or does it not depend on the size? If it does not depend on the size, it means that your small startup company has the same probability to grow as a big company like Nestle, for example. So you can think of this for a moment. Is it true or is it not true? If it depends on size, then we would like to know how the growth rate of a company scales with its size, right? So these are things that we will answer in the lecture and also in the self-study talks. The first step is we need to get the data. There are various ways of proxying firm size, and I will discuss some of these during the lecture. For the moment, it is sufficient to assume that we proxy the firm size by the number of employees that a firm has. But you can also think of other proxies of firm size. Maybe you have a few other suggestions. How can we measure this? Capitalization, right? So that's one. Revenue, yes. So other ideas? Okay. So we will discuss a few, for example, sales is another measure, right? We will discuss some of these proxies, I think, the next lecture or so. The interesting thing I can already tell you is no matter what proxy you use, you'll see more or less the same pattern. So that's why